Hi, this is Mark Weitzman. Welcome back to the fourth video on partial differential equations. And in this video we're going to do problem 8.2 from Mathews and Walker, Mathematical Methods of Physics. So I'll read the problem real quickly. Assume that the neutron density n inside uranium-235 obeys the differential equation del squared n plus lambda n equal 1 over kappa, the partial of n with respect to t, and the boundary condition is n equals 0 on the surface. A, find the critical radius r0 such that the neutron density inside a sphere inside a U235 sphere of radius r0 or greater is unstable and increases exponentially with time. And B, suppose two hemispheres, each just barely stable, are brought together to form a sphere. The sphere is unstable with n equal to e to the t over tau. Find the time constant tau of the resulting explosion. So we're going to use all our tools from the previous videos, and I want to start off just by saying, if anybody thinks I'm giving away any national security information, all of this has been published in the Los Alamos Primer many years ago, and Mathews and Walker itself is from 1971, so all of this stuff is very well known, and it's basically a sophomore physics problem at this point in time. So let's start by starting with part A and using our usual separation of variables technique, and let's write n as being equal to capital N of r comma theta comma phi times t of t. So this is the time function and this is the spatial function. And then substituting this in this differential equation and using our usual trick of dividing by nt leads to the following two equations. Del squared n over n plus lambda equal to 1 over kappa t dt dt, and we're going to set this equal to minus mu as the separation constant, and our other, so we have this leads, we can immediately solve the time equation. dt dt equal mu kt. This is the time part of that equation. That implies that t is equal to e to the minus mu kappa t. So what's going on here, as you can see, is we want this to be, we want to find the critical radius such that if it was just a little bit larger, it would be unstable. That means that it would grow exponentially with time. Right now it's decreasing exponentially with time if mu is greater than 0. But if we have mu less than 0, we'll have an exponential increase. So we really have to solve for mu equals 0. That's the boundary on those things. And this was the time equation. The other equation, this now becomes del squared n plus lambda plus mu n is equal to 0. And this is our Helmholtz equation, which we've solved and we've separated. And we know the solutions to the Helmholtz equation is just n is equal to a product of linear combinations of e to the im phi, e to the minus im phi times, I'm only going to take one of these, PLM cosine theta. I'm leaving out the other one because we're inside a sphere. We need to be regular everywhere, including at the origin, so we only have the non-singular, the regular solution. And then the other part was the spherical Bessel function, JL KR. Again, we're neglecting the NL KR because we need to be regular at the origin. And this is K squared, so K is equal to the square root of lambda plus mu. Okay, so our boundary condition is that n equals 0 on the surface. So that implies that the only way all of these functions can be equal to 0, the only one that has the radial dependence is the spherical Bessel function. So that implies that JL K R0, R0 is the critical radius, is equal to 0. Now, let's define XLP as the pth root of the spherical Bessel function, JLX. Okay? So what we have now is that this implies that KR0 is equal to XLP. Okay, so now we get, which implies R0, substituting for K, square root of lambda plus mu is equal to XLP, which implies that lambda plus mu is equal to XLP squared divided by R0 squared. And this implies that mu is equal to XLP squared minus lambda over R0 squared. So we want to substitute mu equals 0. That's when we'll get to the critical radius. So solving that will lead, well, actually what we want to solve is mu is less than 0. That implies that this is less than 0. And if you work that out, that simply means that lambda is greater than XLP squared over R0 squared, which means that R0 squared is greater than XLP squared over lambda. This implies that R0 is greater than XLP over the square root of lambda. And we really want the smallest value of R0. If we have a value that's slightly larger than R0, if you think about it, it will end up containing components that will become unstable. So we're going to take the smallest value of this, and the smallest value of XLP is when L equals 0 and P equals 1. If you remember when we graphed the spherical Bessel functions, let me show you that graph again. Remember, this time it's the value of the spherical Bessel function, not the derivative. But so the smallest value on these, other than at the origin where they hit 0, is for L equals 0 in the first root. Each root, second root is here, third root is here. This is the L equal 1, the first root is larger. So we're going to have L equals 0 and P equals 1. And you can show, I didn't show it, but in addition to solving just from the software and the graph, you can show that JLX in general is equal to minus x to the L times, 1 over x ddx raised to the L power applied to sine x over x. And this simply means that J0x is equal to sine x over x. And this is equal to 0 when x equals pi. So that's our root. And so our critical radius is that R0 is equal to pi over the square root of lambda. Okay, so let's go on to part B. So what we have here in part B is we have two hemispheres. I'll draw one of them. The radius is RH. And the boundary condition is that n equals 0 on the hemisphere boundary. So this requires that n of r comma pi over 2 comma phi equals 0, because on the flat side of the boundary, theta is measured from the North Pole, so that's the equator, and this is pi over 2. For all radius, even over here it's 0, so it's for all r and for all phi, we have to have that. That's the first boundary condition. And we also have to have that at the hemisphere radius and RH for any theta and any phi were equal to 0. Now, this boundary condition over here, we can satisfy that as before by requiring that JL K RH, we have a different R this time, not R0, KRH equals 0. That will satisfy everything on here. But for the first condition, we have to have that, and if you remember what these functions are, the product of these two are just spherical harmonics. So I'm just going to use spherical harmonic notation. We have to have y LM at theta equal pi over 2 for any phi and any r equals 0. So just looking at the angular part there. Now, to solve this, the easiest way to do it is to just look at a table of spherical harmonics. I just took this from online. And you can see when theta equal pi over 2, by the way, this implies that cosine theta equals 0. So if you look at the first few spherical harmonics, you can see that this is the one. This one will satisfy that because cosine theta is 0. There are other ones. You can go up to the L equal 2, M equal minus 1. That will also satisfy it. But this will lead to bigger hemispherical radius, and the other components, the lower components, will be there and will be exploding otherwise. So in order to have stability, just like here, the lowest ones are 0. So this requires that that we have the same condition as before, and except that this time we're going to have L equal 1 and we're going to take P equal 1. The L equal 1 comes from the spherical harmonic. M equals 0 as well, but that's not important to us. And it's the first root P equal 1 for the J L J1 X1 1 equals 0. Now to get the first root for the spherical Bessel function for the J, again, this one is, we go back to our plot, and you can see for J1 that it reaches 0 at about 4.5. And you can calculate it and solve by software. It leads to the, well, here we can put J1x J1x using this formula is sine x over x squared minus cosine x over x. And this equals 0 implies that tan x equal x. And you can solve for x there. And you're going to get x is equal to 4.4934, I believe. So that confirms what our chart showed, 4.5. So now that gives us RH. So as before, RH is going to be equal to x11 over the square root of lambda is equal to 4.4934 over the square root of lambda. So you can see that for the hemispheres to be stable, it's going to be larger than the sphere. So now when we bring the hemispheres together, we have a total radius for a sphere that's larger than this, and that's the problem, because that makes it unstable. And when you have less uranium, it can be stable, but as you add more and more uranium, it becomes unstable. Too much fissions. The reason why, by the way, the density is 0 on the surface is that on the surface of the uranium, the neutrons are escaping and they don't fission anymore. So the neutron density tends to stay 0 because they escape into the air. Sometimes people put what's called tampers to keep them there, and that lets you use a smaller piece of uranium. But I'm not going to go into details. If you want the details, read that book on the Los Alamos primer. So continuing on with this problem, after the hemispheres are brought together, this is what you have. You have a sphere, radius is RH. On the boundary, n equals 0. We no longer have the condition here. We don't know what's happening here. It's not going to be 0 anymore, because neutrons aren't escaping into the air, and now there's escaping into other pieces of uranium where they can fission. So the density builds up here, and that's what causes the explosion. Okay, so this problem is the same as in this problem, except we're working backwards. Now RH is specified. We have RH. And we need to calculate the other constants. We need to calculate mu eventually, and that will give us tau. So as before, we have nRH equals 0, JL KRH equals 0, KRH equal to XLP. And now the XLP is the same as we had before, because even though when we brought these two spheres together, before we brought them together, we only had L equal 1 components. After we bring them together, all hell breaks loose. We're going to have all components of L. And the one that will explode fastest and will multiply fastest is the L equals 0 component. And so we can calculate from that. So we're going to get the square root of lambda plus mu is equal to XLP over RH. This implies mu equal XLP squared over RH squared minus lambda. This implies, and that's equal to lambda times XLP squared. Now I'm substituting this over here, divided by 4.4934 squared minus 1. And so the time constant, the most explosion will be determined when this is most smallest or when it's most negative. And this will be when this will be most negative when this is smallest. So again, we're going to have, the, as I said before, the same as before. L equals 0, P equal 1, X 0, 1 is equal to pi. So I have mu is equal to lambda times pi squared over 4.4934 squared minus 1. And the time constant tau, we see that 1 over tau is equal to minus mu kappa from there. And this is equal to lambda kappa. I'm going to put the negative sign reversing this. 1 minus I'm not sure I did the arithmetic right here. Okay, yeah. 1 minus pi squared over 4.4934 squared. So tau is equal to 1 over lambda kappa, not k, this is kappa, times 1 minus pi squared over 4.4934 squared to the minus 1. And this gives tau is equal to, if I did my arithmetic right, 1.95 over lambda kappa. So that's the end of this problem, and it's not really that difficult. A lot of these things are just using the boundary conditions, and we've already done the separation, and so you just have to think. You have to think a little bit about what that means and how to implement certain boundary conditions, like the hemisphere is implemented differently than the sphere, obviously. And then when you change things, the old boundary conditions go out the window and you have to satisfy the new boundary conditions. And so I'll see you in the next video. Thank you very much.